Today I have got some very interesting footage to show you. My helicopter of course, and a very special machine. Remember the flying boat Ekranoplan I was building? Well, I was invited to take part in a little get-together. Here we have a completed wing and ground effect vehicle. We are going to see it fly close up. I am going to break some stuff and I'm going to mend some stuff that's broken. This is home-built experimental aviation, folks. Sit back, relax and enjoy the video. The wind today is 7 to 10 miles an hour, so nice and calm. My boat won't fly as I haven't made the wings yet, so I'm just using it to get some nice shots. This is a very well tested and proven machine. It's already completed around 100 miles this weekend. It's a single place, so nice and small, and 3-axis control on this one. My intention is to have 2-axis control. I ask you, how much fun does this look? The cruise speed is somewhere between 45 and 60 miles an hour. You can really get places fast, but it's mainly to just enjoy the experience. It operates only a few feet above the water, making the best use of ground effect. I've seen loads of comments in the past warning of catastrophe if a wing contacts the water, but we can see wing contact here. I asked the pilot about this and he said it's not an issue to touch the trailing edge of the wing. The leading edge would be a different story, but you can't get the leading edge near the water and keep flying. In other words, you would need to crash in order to touch the leading edge.
Right then, finally an update to the flying boat. I haven't worked on this for a year. Been fixing drive shafts, haven't I? I think we need a reminder of where I got to with this. So I took it out on the water without the wings and it seemed okay. 50 miles an hour was the max wing speed. I couldn't turn round in any more than that because the tail weather vanes, you see the tail up there. So that is going to be the wind speed limit. The next stage was to build the wings. So I've got these spars here. That's 4.3 meters from the center to the end of one wing. So 8.6 meter wingspan. I need these struts because these spars aren't strong enough to deal with the forces by themselves. Ideally, I would like a cable coming up from the bottom of the boat up to the spar to take this load, but that's not really possible with this inflatable tube in the way, of course, unless I hooked it to this handle here. Don't think that's a very good idea. So I need struts, and a friend of mine, Martin, has been helping me with the calculations for what size struts I need, so thank you to Martin. It looks like I'm going to need jury struts too, so it's all a bit complicated really. I really like how James Greenberger has done it. He's managed to do it with a cable because he's got something solid to mount it to. That would have been a better design going forward, but let's just learn from this and we'll think about changing things for the Mark II version. What I'm doing at the moment is trying to figure out a nice way to connect this tube to here. It needs to be removable because the wing is just going to be a single skin wing. So they'll just slide fabric over the spar and then I'll put the struts on afterwards with brackets. This spar gets mounted about here I need to make a framework to be able to mount this up here. There'll be another one of these struts going down to that wing. So there'll be a triangular section here with a tube going across so that both wings kind of push against each other. I was just trying to work out what size tube I need to go between the two wings. And that's where I found an online calculator, which is a critical buckling calculator. Lots of calculators online, by the way, if you want to work out tensile forces or centrifugal forces. There's a load of calculators online, which really makes things a lot easier. There's going to be 5.6 tons from the struts pushing on this bit of bar from wing to wing. That's at 2.25 G. I need then a suitable tube that's going to take that load. I looked at the online calculator and it showed that this tube is enough. This is only inch diameter, 1.6 wall. But what I can do is I've got a tensile tester that also does compression testing. I can put it in the compression tester and see how much force it takes to buckle. We have our tube and we have our tester. Now the online calculator said that this inch diameter, 1.6 wall, sorry for mixing up the units there, will take 39 tons, which is obviously wrong. My guess is it will take about 1 ton maximum, I would say. I've got this bit of board here because I don't want to get hit by the thing. It could spring out the way I've got it. That was interesting. It did buckle in the middle. We can see it started to crush at the ends. But it was 2.6 tons it took to do that, which was, yeah, much more than I thought. Next size up then, we have 1.25 inch, 1.6 wall, or 31.75 mil diameter. That failed at 150 psi. We take our piston area, 60 inches squared, times 150 is 9,000 pounds, or 4 tons. Next up, 1.5 inches, same thickness. That last one then, only 4.6 tons. I expected a bigger jump, considering how big a jump it is between those two. Okay, gone up a thickness. This is 3.2 mil wall, 1.5 inch diameter. Now things are getting interesting. We haven't got the crushing on the ends, not quite like the others. And the pressure, 443 psi, which is 12 tons. Hopefully this is the last one. 50.8 diameter, 3.2 wall. Well, that wasn't much better, only 13 tons. I want something stronger than that. Here's the reason. The length I'm testing, which is the maximum I can fit in that machine, is only about half the length of what I actually need. And the buckling strength reduces by the square, I believe. If I double the length, I need to quadruple the strength. I need to make something to balance the prop on my boat as it has some damage. JLCMC sell ball screws, linear rails, and as we already know, ball splines, but they also sell precision ground shafts. This is just what I need to make a prop balancer. Lengths are available up to 1520mm and 50mm diameter. There are two classes of precision available along with material options and surface finish including chrome plating. They also offer custom features such as internal and external threads, machine flats, ring grooves and keyways. If you have a project in mind using these linear shafts, I'm sure JLCMC have what you want at a great price. As always, the parts ordered arrive quickly and are well packaged. And there is the finished prop balancer. It's very evident these shafts are exactly what I ordered. They are high precision, straight and hardened. Perfect! Check out JLCMC for all your mechanical parts needs. Details and coupons in the video description. Thanks very much to JLCMC for sponsoring this video. This is what I've come up with for the wing strut as a joiner. It's all aluminium, 6082T6 will be the grade, and it's got M10 bolt going through the centre, which is, by my calculation, rated for 6 tons. It will have 3.7 tons maximum. What I really like about CAD is we can check everything moves as it should. You can see if we articulate the joint there, it hits about there, and that's the maximum angle before we have a problem. There's only going to be 22 degrees I think needed, so we've got plenty of angle there before it touches. And of course we can check the weight. Just over 300 grams is what the complete joint weighs minus the bolt or pin. We need 4 of these complete and 4 half units, so it does add up. There was a comment in the last video that might make me look a bit stupid. It's a bit hard to admit to doing stupid things on YouTube because I know I'm going to get a few comments saying, that was stupid. Yeah, I know. Talking about a tail heavy condition, and when I did the hang test, it wasn't tail heavy, but in flight it was. There was one difference someone pointed out to me, and that is the skids, the long bars or poles to stop me tipping over. I didn't have them on when I was doing the static hang tests. Now that shouldn't make a difference, but the landing gear or legs should be in the middle. They should be in the center or should line up with the mast, and they don't. The mast is slightly forward or the legs are slightly backwards, and that means it's going to hang low at the back. Okay, 0.35 tail heavy. Not as bad as I thought actually, but well pointed out. The skids need to move forward a little bit to make this right. The next thing then, the switch that got hot. I pointed out it was 25 amps. It also says 12 volts right next to it, so I would assume that is DC and not AC. I think then it was the connector that caused this problem. The current draw through this switch is 18 amps. These are Luca connectors, and I think if it was the Luca connector, there's no point putting a relay on that uses the same connectors. On the advice of a very knowledgeable chap called Donald, he suggested using this push-pull type switch rated for 75 amps, and it's got the screw type connectors. I think that is quite a good solution. Only weighs 59 grams. Here is another solution by a viewer. Suggestion was to use water wetter in the coolant system, and that should improve the efficiency of the heat transfer. Never used this stuff, worth a go, isn't it? It's a very attractive bottle. I had to resist drinking it. Actually, we've had a very hot summer here. I wonder if drinking it would have cooled me down. Here is something interesting. I've mounted a bar from the rotor head going down, and that is just to get a feel for what that kind of arrangement feels like. This type of control has been used by the Benson B9, the Gen H4, and JP Crocker on YouTube has also demonstrated the use of this type of bar very successfully. They have all achieved much more than I have. And the advantage of this is that it's simple, it just bolts straight to there, there's no linkage, there's nothing to go wrong. The only issue is everything is backwards. So forward is backwards, left is right, and right is left. I'm wondering if the stick force is less with this long bar coming down here than it is on my mechanism. Let's find out. Got to figure out how to get in here first. Ooh. There we go. Right. Okay, so that would be backwards. That's backwards. Yep, stick backwards. Forwards. That's forwards. It's a little weird. What's that? Left. Right. Yeah, okay. Still feels quite heavy, to be honest. What's that? Oh! Ah! Oh, that wasn't funny. Jeez. You don't want that happening in flight, do you? Right, here we go. Right. I'd say left to right is easier with this one. Yeah, I'd say so. That's not an advantage then, is it? Yeah, I'd say forward and backwards is too. The early gyrocopters were also controlled with an overhead stick where everything was backwards. I've seen some people say that they can transition from an overhead stick to a conventional without any issues. If you had two hands on, that may be an option. You'd have to have the throttle on, I don't know, quad bike type throttle or motorcycle lever or something. I'm worried about that G-clamp now. You stay on there. You're going to stay on there, are you? I mean, if this was extended down, I don't know. I'm thinking that my conventional stick is fine. Ah! Right, I've had enough of this. It's too painful. If that overhead stick reduced the amount of force it took to control the rotor, then I would have definitely given it some serious consideration. At the moment, I'm not convinced it's the right way to go, which is kind of unfortunate because it's so simple. I've just found a fracture, and there it is. It's on the front leg. It is broken all the way through. The other one hasn't, but I suspect it will do. The question is, why? If we look at the other one, not sure if you can see it, but that is bent in the forward position. From here down, it's bent that way. This means that the framework is flexing back and forwards. If we go back and look at what could cause that, it's the tail. What I think is happening is the transom is going back and forwards with the tail going up and down, all that leverage. It's transferring through this tube down these cross-section bars to there, and the weakest point is right there. Let's set the camera up so I can see when I flex the tail what's going on. question now, of course, is how to solve it. Now, I've put this cross section here in because I knew there would be force going along here, down through there, down to these attachment points, but it's obviously not strong enough. So I'm thinking maybe attach to this bracket here, which was there from when it was a fib, flying inflatable boat, attached to that bracket, perhaps up to these brackets at the top. That's what I'm thinking. That would probably be the lightest solution. You don't really want to be making these thicker because it will still break, it will just take longer. Or maybe a tube from those two bolts there up to there. I wonder if that would solve it. Here's what I've made to balance the propeller. Now these hardened shafts are very straight and they're precision ground. So it's very sensitive, more sensitive than my inclinometer. I've got these adjustable so I can set them level so they're not influencing the balance at all, but it's more sensitive than my inclinometer. I made this adapter so I can come off the same position as the propeller is mounted on the engine. There's no play in this. You can see the fit I've got on that. It's just a tap-on fit. That's bolted up now. We just need to wait for it to stop moving. Now that it's finished moving, we can see that that blade is the heaviest, but it's not in the vertical position. It's slightly offset. Not quite sure what that means. Maybe the spacing between each blade is not quite perfect. But what I'll do is I'll add some weight to that blade and maybe that blade as well. See what happens then. I've already numbered these blades, so the heavy one is number 2. I think what I'll do first is just put a bit of tape on this blade and see what happens. Okay, what that bit of tape there has done has brought this blade further this way. Now I need to add another bit of tape to this until this is vertical. And then we know that if we add weight to that one and that one, we are balancing the system. The objective in the end is to have it so that it won't stop at any point. It's totally random. I've added about 4 bits of tape more to that one, and now this blade is hanging vertically. Now we can add weight to those two and try and balance it. What I've done now is I've put an M5 washer on both blades. But that isn't enough. If we do a little test here, this is the heavy blade. If I push this up just slightly, it reverses and goes back down. So it's still too heavy. Or these two blades still aren't heavy enough. I've put 2 M5 washers on these two blades. And now we've got a change. So do the same test again, just hit that slightly up. It continues going up. Now it appears that blade number 3 is the heaviest by a small margin. I can just peel off one bit of tape and we'll see what that does. Forgive me, I'm just trying to work this out as I go along. Never done this before. So I could be doing it completely wrong. I think we're getting closer. I think add a tiny bit of tape to that one, but I'm not 100% sure. Now, when I spin it, it stops in a different place each time. I think that means it's balanced. And all I need to do is take these bits of tape and washers off the end of the blades, weigh that, mark the blade, and that's what's to add. I have been waiting for a good day to do some more hovering, but the last 3 weeks hasn't been any good. Winter is approaching, but I'm sure there'll be opportunities before things get too cold and wet. With regard to the online buckling calculator and the figures being out, I think there is a point where the tube crushes rather than buckles. The shorter a length you input, the more ridiculous the result becomes. I do think it's accurate for longer lengths, but how it's mounted makes a big difference to the buckling force. For example, if the ends are fixed or able to pivot. As always, thanks for all the help. See you in the next one.